So it's an honor to introduce Luca Carlone. He's assistant professor at the Astro department at MIT since 2017. And in his career, he got his PhD from the Politecnico di Torino.
Fantastic.
There you
yes.
go.
Very good.
In 2012, and then he spent a couple years at Georgia Tech as a postdoc, and a couple years at MIT and Leeds as a research scientist, and then he started as faculty. Throughout that process, he's been sort of interested in many kinds and types of estimation problems. Maybe this is an oversimplification, but different trade-offs between practical algorithms or optimal algorithms or robust algorithms or physically constrained algorithms when you have limited computation, exploring many of these trade-offs for, at the end, coming up with good estimation algorithms. Work that has been widely recognized with Best Paper Awards at the Workshop on Algorithmic Foundations of Robotics, and also at with the Best Paper of the 2017, the Transaction of Robotics, a very highly rewarded journal. So we've been working on many estimation problems, as I was saying, many different practical applications, right? So all the way from estimating in complicated manifolds like the special Euclidean group, as well as estimating the poses of objects, something that maybe might be more visually understandable for the mundane people. But at the end of the day, it's like the understanding of how data turns into a state. So it's an honor to have you here, Luca. Thank you very much. So please.
Wow, too kind of an introduction. Thanks, Alberto. Thank you guys for being here. You cannot imagine how much of a privilege it is to give the robotics seminar at MIT. I'm thrilled. Today I'm going to talk about certifiably-robust spatial perception for robotics. As Alberto said, I started at MIT as a faculty 1.5 years ago. And what I did at MIT is to create the Spark Lab. Spark stands for Sensing, Perception, Autonomy, and Robot Kinetics Lab. And the mission of my lab is at least pretty simple on paper, is to develop theoretical understanding and practical algorithms to bridge the gap between human and robot perception for autonomous navigation. I'm sure that this audience knows what is perception, but for those of you who don't know, you can think about this cartoon in which imagine that there is a robot sensing the external world, the real world, with some onboard sensors. And perception is a set of algorithms and hardware processing the sensor data and some prior knowledge to get an internal model of the external world. You can imagine that perception is essentially a broad umbrella for a number of challenges in signal processing, like computer vision, in state estimation, like localization and mapping and 3D computer vision, probabilistic inference, machine learning, and so on. So my lab really cares about perception, and I want to give you two practical instantiations of perception problem that we care about. The first one you guys will be familiar with is simultaneous localization and mapping, SLAM. In this case, you deploy a robot in a completely unknown environment, in a GPS-denied environment. And the robot is in charge of reconstructing a map of the environment while figuring out its trajectory while moving in this unknown environment. This, by the way, is an example from a project I'm very excited about. We are part of the DARPA Subterranean Challenge in collaboration with JPL and Caltech. And this is some experiment in which we are mapping this underground cave. So, of course, for this case, I'm doing mapping with the LiDAR sensor and this kind of robot. But, of course, you can imagine that SLAM is a quite general technology that will apply also to different types of sensor and different types of robots. All right, so example one is SLAM. Another problem that I'm going to touch upon today is object pose estimation and object detection. And in particular, I'm going to talk about the registration problem, which is about finding the rigid transformation, which is a position and rotation that aligns 2 point clouds. This is a typical problem that shows up when I give you a template, an object that I want you to recognize, and I ask you to find that object in a big point cloud. Of course, typically, you don't care too much about the serial box. A more practical instantiation is the case in which I give you a Velodyne LiDAR scan. You have to look for a car, for example, for a known object. So, couple of examples here of perception, and I want to stress for a few minutes why perception is really important for robotics. Let me start with an application we're all familiar with, which is self-driving cars. You can imagine that for a self-driving car to operate safely in the environment, the car has to figure out the lane boundaries, pedestrian crossings, the position and the presence of other cars, potentially track the speed of other cars, detect traffic lights, and potentially reason in terms of the intentions of the other cars. Well, these are all perception problems, okay? And in general, besides this application, perception is needed for situational awareness, obstacle avoidance, and to support planning and decision making. Beyond the example of self-driving cars, it turns out that recent advances in algorithms and computation for perception are making possible a broad number of applications. So perception algorithms is steadily transitioning from academic research to products. And you can see these in domestic robotics application, industrial robotics, search and rescue and disaster response with drones, and even applications that traditionally are not associated with robotics, like virtual and augmented reality. So the good thing is that whatever research we are doing in robotics nowadays is having a huge impact on society. It's getting really a practical impact on society. The bad news is that the broad adoption of these technologies is also showcasing a number of limitations of existing algorithms. And in particular, you guys might be familiar with a number of failure modes here. This is a Tesla accident in 2018 in which the computer vision system misclassified the concrete obstacle here on the left and decided to turn into the obstacle just because of a failure of the perception of the computer vision system. And this is another popular example. How many of you have seen this? Good portion. OK, so this is a case in which stop sign in nominal condition, a neural net is able to detect and classify a stop sign. But if you carefully place these markers on top of the stop sign, you can mislead a neural network to think that this is a 45 mile per hour speed limit, which is a pretty bad mistake to make an intersection. And there are multiple examples of failure also in problems related to object detection, object classification, pedestrian detection. One thing that is quite surprising is that even very established products like Google Street View, if you spend enough time on the internet, you will find examples of failures of Google Street View, as in this case. And it turns out that Google has a huge amount of people just in charge of verifying and sanity checking the maps and fixing them manually. Okay? So what I want to say here is that despite the fact that this technology is starting to have an impact on many practical applications, there are still fundamental limits, and ideally there is we really would like to go beyond this kind of manual human supervision. Okay? So far I should have convinced you guys that perception is important for robotics. And what I want to do in the rest of this talk really is two things. I want to go over a number of key challenges in perception. I want to give you like a broad overview of what are the key challenges, which is also an excuse to tell you about the work that we are doing in my lab. And the second part of the talk is really about focusing on a specific challenge, which is Outlier-Robust spatial perception, and tell you about two contributions, recent contributions from my group, which I'm very excited about. Feel free to stop me at any point. So let's start with key challenges. So in my opinion, a good way to think about key challenges is to think about what are the axes of complexity of perception. And here I'm putting like three main axes of complexity: robustness, efficiency, model complexity. You can imagine that if we go along the robustness axis from left to right, we are trying to design algorithms which are more and more robust to noise, outliers, attacks. If we go along the efficiency axis, we are trying to design algorithms which are more and more efficient. So they take less power, they require less, smaller hardware, or they are just faster. The third axis is a little bit less intuitive. It's about model complexity. So you can imagine that as you go along this axis, you are building richer and richer representation of the world. So here you are building a very simple model of the world. Here you have like a very rich understanding of the external environment. To understand a bit better this axis of complexity, let's try to populate this with few examples, just for the sake of the exercise. And you can imagine that human perception is probably up there. Human perception is a pretty efficient perception system. The human brain works on 20 watts, which is a very good, very efficient embedded system. And robustness is also pretty good. I can show you optical illusion to trick your perception system, but in general, it's pretty hard to confuse you. Like with your perception system is pretty robust. And of course, you have a very rich representation of the world. You can imagine that if you close your eyes, you have a very complex model of the environment around you in terms of the geometry, presence of people, and so on. If you try to repeat the same exercise for the state-of-the-art in robotics, you can start with the Roomba, very popular robot. It turns out that the Roomba is as efficient as a human. The Roomba is probably 28 watts power consumption, which is comparable to the human brain. That's a bit disappointing, I guess, as a data point. But and in terms of robustness, of course, the Roomba is not designed really. It's designed to be cheap. It's not designed to be very robust, to build a complex representation of the world. Other data points, state-of-the-art in drone technology, the SkyDR1 drone, more expensive. So we'll get like a more complicated representation of the world. Extra robustness, because you don't want to break this, probably $2,000. And that will come at a price of efficiency. You iterate this exercise, you put here self-driving cars, Google Street View. And by interpolating these data points, what you can see is that there is a very intuitive trade-off here going on. The intuitive trade-off is that nowadays in robotics, if you try to design systems which are more robust and gets a more complex representation of the environment, the efficiency of that system goes down, which is a very intuitive trade-off, right? The thing that is interesting is that humans somehow are defying this trade-off or are just finding a much better Pareto curve out there. And really the goal of my lab, and I believe part of the goal of people doing perception in general is about bridging this gap right now. So in my lab, we're working really across all the spectrum along these three axes, pushing the boundary along these three axes. And I want to tell you about a few things about work we're doing in efficiency to improve efficiency, robustness, and high-level understanding. In terms of efficiency, we're exploring this notion of visual attention. The basic idea there is that the key to be efficient is to be very selective. You're not efficient by processing every bit of data. You're efficient by selecting what are the subset of bits that you really care about, which is the notion of attention in humans. Okay? We've been working on a notion of visual attention, for example, for SLAM, or visual inertial navigation. Along the efficiency axis, we have been pushing the boundary also with contribution, which are not really algorithmic, but are really about chip design in collaboration with the other faculty at MIT. And of course, you can think about the notion of efficiency being applied also to multi-robot system. In this case, being efficient means really reduce the amount of communication that you have in multi-robot system to get essentially multi-robot mapping in this case. Put a lot of work on robustness, I believe, is one of the key problems, the key issues here. And we investigated robustness, in particular in SLAM problems, robustness to large noise and outliers. And these will be like essentially the topic of today's talk. And we are getting more and more interested in high-level understanding. So we are looking at how to be clever in formulating optimization problem to get very fast 2D semantic segmentation and 3D semantic reconstruction. Okay? These are just a couple of examples. What we really want to do eventually is to understand how to exploit semantic understanding to improve 3D reconstruction of the environment. OK, so let's jump right in the topic, the technical topic of the talk. Today I'm going to talk about outlier-robust spatial perception. And I'm going to touch on two main contributions. One, which is about some fundamental property of the outlier-robust spatial perception problem. And the other one is proposing algorithms to solve it. So why do we care about outliers? Why is it important to deal with outliers when you do spatial perception? I want to convince you that outliers are very important to analyze, to investigate in the context of the simultaneous localization and mapping problem. So how many of you are familiar with SLAM here? OK. So for those of you who are not familiar with SLAM, what you see in SLAM is that you have the robot going on and exploring this environment and building this 3D reconstruction of the environment. But really, in the background of a SLAM system, what ends up happening is that you're trying to solve an optimization problem. This is what is called the maximum likelihood estimator. You solve this optimization problem to get an estimate of the trajectory of the robot. And once this trajectory of the robot is reconstructed, it's easy to build a map on top of it. So this optimization problem is trying to compute a set of poses Ti, poses position and orientation. And imagine that these poses are dropped along the trajectory of the robot. And it's doing so by minimizing a non-linear least square problem in which the Tij bar are the given measurements. So you try to compute a set of poses along the trajectory of the robot given these relative pose measurements. So where do we get these relative pose measurements? Let me try to explain using this figure here. Imagine that you have a robot, again, traversing a completely unknown environment. We really would like to figure out the trajectory of the robot as a discrete set of poses. And what we can do is that we can compare sensor data at pose I and j, and somehow we can do some magic trick. We can apply some algorithm to compare this sensor data, and out of the comparison of these two sensor data, we can get a relative pose estimate, Tij bar, which is the relative pose between pose I and pose j. And really, SLAM is about figuring out the trajectory of the robot given all these relative pose measurements. You can visualize this problem as a graph in which you have a measurement for each edge in the graph. That's the Tij. And you want to figure out quantities, poses at the node of the graph. These are the T1 to T7 in this case. So this is a standard SLAM problem. It's one of the most popular formulations for SLAM, which is known as post-graph optimization, post-SLAM, or graph SLAM. And really, given the Tij, assuming that the quality of the Tij is good, in some sense, this problem can be considered solved. It's well understood how to do this optimization, to solve this optimization problem, even though this is a non-convex problem, because the set SC3 is a non-convex set. The set SC3 is the set of 3D poses. And even though the cost function here is just a quadratic function of the poses, the non-convexity of these makes this a challenging problem. But it's well understood by now how to solve it. So the challenge here appears when we want to do SLAM in the presence of outliers. Outliers clearly are bad measurements. And where do these bad measurements come from? So imagine that I'm exploring the cave. So my robot is exploring this cave. It's starting at some pose T1. It's moving at pose T2, T3, T4. At pose T4 is taking this sensor measurement. It's taking, let's say, this image of the cave. And then it keeps going. It keeps walking along the trajectory, going to T5, T6, and T7. Arrived at pose T7, the robot is collecting another image of the environment. And just by coincidence, this image really looks like it's a cave, really looks like the other one that we collected at T4, even though these are two completely different places. So the robot is confused to think, is misled to think that this part of the environment is the same as that, just because they look similar. And what it's trying to do is to enforce a relative measurement between these two poses, even though these two poses are really far away. They have nothing to do with each other. So this is what is called an outlier. And by the way, that's very similar to what happens for humans. If you walk in a cave and your place recognition system fails, you can just get lost for the same principle here. So why this kind of phenomenon in which you have outliers? Why is this a problem? Well, if you feed an outlier to the optimization problem, I want to show you what happens. So let's start with the case in which you have a bunch of measurements Tij bar, and there is no outlier. So they're all good in some sense, meaning that they have Gaussian noise, essentially. Without outliers, you solve this optimization problem, and you get a reconstruction of the trajectory of the robot. This is a discrete set of poses, but I'm just visualizing it as a continuous trajectory. And I can guarantee you that that's the right reconstruction of the trajectory. That's how the trajectory looks like. Now the problem is that if I just add 5 outliers, 5 random outliers to this set of measurements, the same trajectory, I feed 5 outliers to this problem, I try to solve, and I get this reconstruction of the trajectory, which is completely different from the actual trajectory of the robot. So I'm not really able to get a good reconstruction of the environment. if I have 20 outliers over like a total number of measurements, which is around 3,000 measurements, so it's a huge number of measurements and small portion of outlier, you can see that the reconstruction of the trajectory is completely off. So 2 observations here. The first observation is that the incapability to detect and reject outlier results in complete failure. You can see this from here. And the other observation is that we started with a problem that was already non-convex because of the presence of poses and so on. And now with the presence of outliers is even combinatorial, because somehow you have to figure out which one is inlier and which one is outlier. So there is a combinatorial nature. So this makes for a really tough problem to solve.
Is it clear even what problem you are trying to solve? Or can you write down the correct
Yeah,
objective?
we'll write it down in a few slides. Yeah, but the bottom line here is that these definitely will not give the right solution. Yeah. OK, so before trying to write it down, we would like to see like what happens in practice, how essentially existing libraries are dealing with this problem of outliers, and if this is really a problem. So what we tried here as part of the graduate class I was teaching last fall is to introduce a little bit of mapping of the MIT tunnel system using existing state-of-the-art tools for SLAM. So we use Google Cartographer and OrbSLAM to do this exercise in mapping. And what happens is that if you just try it without spending too much time on the tool, you just try doing mapping in Google Cartographer, you get this type of map instead of the actual map of the MIT tunnel. Who did this during VNAV? Yep. So Chris knows about this. If you spend more time here, instead you use OrbSLAM, and you spend more time in doing a lot of parameter tuning and very careful data collection, you can get a much better map here. You can see the different segments and so on. This actually is still off a little bit, but looks pretty good overall. And that, to me, is really the status of the SLAM problem and many spatial perception problem. So the state of the art is that algorithm kind of work, in the sense that if you spend a lot of time doing parameter tuning and you are really careful in the way you collect the data, you can get reasonable results. But unfortunately, my point is that kind of work is not a good answer if you're dealing with safety-critical application. And also, it's not a good thing that we have to be so careful in collecting the data to have a good result. It's like, we don't want to walk too fast because essentially our perception system can get lost. Doesn't make sense. We don't want robots to be like that. We can look quickly at what is the state of the art instead on the research side, on the academic side. I'm listing 2 sets of works. There is a lot of work done. So 2 sets of work I'm listing is about using robust estimation in conjunction with some nonlinear optimization technique or looking at measurement consistency. And I don't want you guys to parse too much out of these, but these are example of failure modes of 2 existing algorithms, Vertigo and RRR. The issue that I have with the state of the art are these 2 aspects. First of all, again, we get this issue that existing algorithms rely on existing extensive parameter tuning. And parameter tuning is not bad in general, but the problem with parameter tuning is that in this case, the parameters you have to tune do not have a physical meaning, which means you have no guideline on how to tune them. And the second aspect is that the parameter tuning is scenario dependent, meaning that if I have to run my robot at MIT, spend 2 days doing parameter tuning, then I go at another place, and that doesn't work. The second issue is that most of these algorithms rely on some iterative optimization technique, which require an initial guess for the trajectory. And so the quality of the result really depends on the quality of this initial guess. And there is this risk of cascade failure, in which if at some point you accept a single outlier, your trajectory guess gets much worse, and you tend to accept more and more outliers. So you just have a cascade failure. What I want to stress, finishing with the motivation for what we want to do, is that being conservative here is a failure mode, in the sense that it's not only a failure to accept outliers, because that leads to wrong trajectory estimate. Another failure is being incapable of capturing inliers. For example, this is another experiment for the DARPA Subterranean Challenge, and we spent so much time doing parameter tuning and making sure that we didn't get outliers in our estimate that the robot is really trying to force measurements saying that this corridor is the same as that corridor. but all our tests are just rejecting that as an outlier. And this, again, is a failure mode. So what we want is really two things. We want optimal algorithms, and optimal means algorithms that are able to reject all outliers while keeping only liars for some definition of outliers that I will give shortly. And the second is really, we don't want parameter tuning. We just want algorithms that do not rely on expert parameter tuning or careful data collection. So what we did, really, any questions so far? I know that was kind of a long introduction and motivation, but we'll get to the point. OK, so what we did seems is an interesting problem. There are like a lot of practical application, and there is no good solution, in my opinion, out there. So we tried to approach the problem, and I believe the good, reasonable starting point is to say, can we even hope to formulate and solve this problem? So what we did, as Luca was suggesting, is to look for, first of all, to start with a general formulation of the problem. In the outlier-free case, there is a general formulation. So spatial perception problem in the outlier-free case are commonly formulated as nonlinear least square problems. And in this kind, in the absence of outlier, essentially, this nonlinear least square, again, you want to compute some state x belonging to some domain. And you want to do that by minimizing a sum of squares of the given measurements, where the yi are the measurements, yi is the height measurement, and hi is the residual error. You can think about the residual error as capturing how well the x is explaining the y. I also said that this formulation typically doesn't work, and I want to give you like a very intuitive reason why this doesn't work. So you can see here that there are squares, right? So there is a quadratic dependence between the residual and the cost. So you take the residual, you square it, and you put it into the cost. What happens there is that outliers, pretty much by definition, are measurements with large residual. And the cost is quadratic in this residual. So outlier end up dominating the cost. That's why it doesn't work, this kind of estimation problem with outliers. Our formulation looks like that. We said, let's consider a general formulation for outlier rejection, and this is how it looks like. So here, not only you minimize with respect to the state that you want to compute, but you also minimize to find the set of outliers, so the subset of measurements being outliers. And you do that in order to minimize the number of outliers. You want to pick the least amount of outliers to avoid rejecting good measurements. But the condition is that whatever measurement that you consider in liar, so the set of measurement minus the outliers, whatever measurement you consider in liar should have small error. Okay? So in other words, again, we try to find the smallest set of outliers such that the remaining set of measurements can be well explained by a state x. Why we did this? Well, I believe the real reason is that this formulation is quite general, and is including a number of standard formulation in the literature, including consensus maximization, which is very popular in computer vision, truncated least square, which we'll see in the rest of the talk, and other formulations. Now it gets to the bad news. Well, the bad news is that we try to analyze this optimization problem. We try to find if it is even possible to solve this optimization problem. And we incurred in approximability result. So the key result says informally that problem 1 is not approximable. In the worst case, there is no polynomial time algorithm that can compute a near optimal solution to it. The more formal statement says something a bit deeper, I guess. If m is the total number of measurements and O star is the optimal selection of the outliers, then there exists a polynomial function k, a function epsilon, and an instance of this problem, such that no quasi-polynomial time algorithm can compute a solution which costs smaller or equal than k1 times the optimal. So O star is the optimal solution, and any quasi-polynomial time algorithm cannot even get close to O star. It's k1 times away from O star. Okay? And for those of you who don't know, quasi-polynomial time algorithms are essentially slightly slower than polynomial time, but faster than exponential. So this is saying, in the worst case, we do not have any hope to really solve this problem, even close to optimality. And here, close to optimality means a very precise thing. We cannot hope to find the outliers and reject few inliers. That's what it means. Questions?
Is this sort of the right problem to be solving? Like, where does epsilon come from? And let's say you've just chosen the optimal set of outliers. Aren't there a variety of x's that are, solutions to this? Because you're sort of not directly penalizing, you're just constraining that to be less than some value, the hi squared instead. Can you have that in the objective as well?
Yeah. So variation of these will also, following the same reason, can also be shown to be inapproximable. For example, something that we'll do next, which is reasonable to do, is that you say that rather than the sum of the square is smaller than epsilon, you can say that each measurement should have a residual smaller than epsilon, which means you define what is a measurement, saying that what is an inlier, saying that an inlier is a measurement with the maximum residual epsilon that you decide. So a translation error, the maximum I can tolerate is like 10 centimeters. You can say that 10 centimeters is a bound. You can follow the same reason, and you will still get to an approximability. So, so far, pretty bad news. It is impossible to design an algorithm that in every instance of outlier rejection will work well, because polynomial time algorithms will work badly in the worst case. So we can just give up and say, OK, we cannot solve this problem. Let's do something else. What we propose is really like a change in perspective here. We propose this idea of certifiably robust algorithms, which I believe is a very interesting concept. Essentially, since you cannot solve every problem instance, we just want algorithms that can assess their performance in each problem instance. In other words, we want an algorithm that works well and certify that it is working well in common problems, the one that you encounter every day when you operate your robot. But at the same time, the algorithm should be able to detect and declare failure in worst-case problems. Should not just fail silently, should say, I'm not able to solve it. And anyway, that's pretty much the best you can do, because in the worst case, it's impossible to get a polynomial time algorithm. And of course, one requirement here I'm putting is kind of implicit. The algorithm should be polynomial time, right? We are doing this to get efficient solution. Seems to be quite interesting concept, but it's unclear if this is even possible to do. Is it possible to design these certifiably robust algorithms? Well, the fact that that's the item in the next part of my talk, probably the answer is yes. We can design certifiably robust algorithms. And in the following, I'll provide two examples. First one is about certifiably robust SLAM, and the second one is about certifiably robust registration. Okay? I will show that it is possible. Certifiably robust SLAM, we started with the nonlinear least square function, and we said that this is not going to do it. So we consider a variation of the formulation that I showed a few slides ago. So we consider a truncated least square formulation for SLAM. Truncated least square, you can see that this is pretty close to the formulation that we proposed, but instead of having like a square of the residual error, you put the residual error as argument of a function, where the function is a truncated quadratic cost. Rather than being quadratic all the way, it is just constant outside a bound. So the function, again, fc is quadratic if the argument is within some bound c and is constant otherwise. So why does this make sense? Well, it has two desirable properties. First of all, the truncated least square tries to maximize the number of inliers. Why is that? Well, you can see that inliers are the one falling in the quadratic region, and the cost is smaller in the quadratic region than in the constant region. So the cost will essentially enforce that you pick as many inliers as possible. And by construction, the one that fall in the quadratic region have residual error which is smaller than c bar, the maximum error that you want to tolerate on some inlier. Okay, so it has these two desirable properties. And note that this is essentially a way to get rid of the fact that outliers with large residual error are dominating the cost. Now, instead, outliers with large residual error are just having a constant impact on the cost. So we really address this issue and having the presence of outliers. So now I'm telling you that this is a reasonable formulation to try to solve to get robustness to outliers. Unfortunately, this formulation is not the nicest one, because the function fc that I'm showing here is this quadratic, truncated quadratic term. For those of you who are familiar with optimization, you realize that it is a non-convex, clearly a non-convex function. and it is not differentiable. That can be or cannot be a problem. So essentially, what I'm going to do in the next few slides, I will show you that actually it's possible to get global solution to this optimization problem, even though the formulation to start with looks ugly, looks very difficult to solve.
Is there a reduction from this objective to the yes, that's that.
Yeah. So we don't hope to solve the worst case of this. Yeah.
Not only is it non-convex, but if your initial guess is far enough off, then the gradient everywhere would be zero. So.
Surprising that disappears as a problem. I will show you, like, we will get a convex relaxation, a few slides of that, and does not even show up as a problem. I'm very surprised, but I agree. So that should show up, the fact that you have flat gradient, but it's not really a problem. You can just solve it, and I will show you how. The first insight is something that you can do in high school. I think it's like a very simple one. You can just rewrite this cost function, which I wrote as a quadratic in some region and a constant otherwise, by introducing additionally binary variables. So I'm just rewriting the same function there with binary variables. So you can imagine that the theta as a binary variable can be either -1 or +1. If the theta is +1, you get the quadratic behavior, and this guy disappears. And essentially, you are inside the quadratic region. If instead the theta is -1, the first term disappears, and you get a constant, so you are in the constant region outside. In other words, the theta is deciding, theta +1 is saying this is an outlier, theta -1 is saying this is an outlier, should be like out of the constant region.
So the selection of C bar, is it data dependent or
is a constant that is the only threshold that you have here. Is the maximum error that you can tolerate to call a measurement in liar. Okay, so that's the first step. So we started with a weird problem. We made it a little bit more complicated by also including binary variables. So let's try to see how this problem looks like if we use this expression of the cost function. And that's shown like in this optimization problem. Despite the complexity of the optimization problem, it's pretty easy to understand. Again, like, if theta ij is +1, you keep the quadratic term. Otherwise, you delete it and you set it constant. And you can visualize this graphically as a discrete continuous graphical model. So in the previous slide, I was showing you the graph of poses that we are doing estimation over. And what I'm saying is that now we augment this estimation, this graphical model, with a binary variable associated to each age. And these binary variables will decide whether that measurement is an inlier or outlier. This is what we call the discrete continuous graphical model. For those of you very familiar with SLAM, you will say, well, but this idea is like, switchable constraint is very close to other formulation. And indeed it is. Like, the basic idea of including binary constraint to switch off variable is very common. What we did so far, first of all, is to get to a slightly different expression, in particular for the second term, which will help us. But also, essentially, we are providing a unified view. So we're saying that while switchable constraint, the paper was calling this some probabilistic prior on the activation of the constraint, we are demonstrating that this is only writing a robust cost function. So now the C has a clear physical meaning. It's the maximum error that you want to tolerate on the inliers. So that's cool, but it's not like fully satisfactory. Ideally, we really want to solve this optimization problem, which is what we try to do next. So next, I want to show you how to get a global globally optimal solution to this optimization problem. The insight that you have here is that all the constraints in this optimization problem can be written as quadratic equality constraints. The constraints are a bit hidden here because they are really like, hidden over here. The first constraint is that Ti are poses, so they're a member of SC2 or 3, depending if you're on a planar setup or 3D setup. And I'm arguing that that can be written as a quadratic equality constraint. And indeed, if you have a pose is just a rotation and a translation. A translation is a vector which is unconstrained, so we do not have to worry about it. And a rotation is some orthogonal matrix, in the sense that rotation, by definition, should be orthogonal, which is R transpose R equal to the identity matrix of the right dimension. And for those of you who are a bit more expert about this, I'm dropping the determinant constraint for simplicity, okay? So because a rotation should also have some determinant equal to +1. The second constraint that we have is this fact that the theta ij should be either -1 or +1, and it's pretty easy to realize that forcing the theta ij to be binary is the same as forcing theta ij squared to be 1. The only solution to that equation is like -1 or +1. So I'm seeing that all these constraints can be written as quadratic equalities. And the good thing here is that although quadratic equalities are non-convex, are still non-convex, they are amenable, they are good to do like a convex relaxation. So what we are going to do next is to move from these non-convex, the starting problem, which is non-convex and very difficult to optimize globally, to something that is a convex relaxation for which is, you can get to the optimal solution in polynomial time. How do we do that? Well, this is next 3 slides, probably. If you're not familiar with optimization, you want to cover your eyes. So that's like, the denser part, but I would like to show you that, the math of getting the convex relaxation is actually, is a lot of algebra, it's pretty simple. So you start with this optimization problem. The first thing that you do is you try to reparameterize the optimization problem in terms of a variable x, where x is always stacking all the unknowns, rotation, translation, for all the poses, and the theta's, okay? We're just stacking all in a single large matrix. Then the second observation is that if this is x, which is stacking all the variables, x transpose x is just, if you do the matrix product, will be just containing all the product within pairs of variables. That's the way like the product works. And finally, the observation is that you can rewrite every part of this optimization problem as a function of x transpose x. So you can write this optimization problem by using some entries of this x transpose x. The objective in particular will be a quadratic function of x transpose x. I will not do the demonstration for that because it's a little bit algebraic, but I would like to show you is that the fact that, for example, rotation should be orthogonal just means that we should pick, for example, the diagonal blocks of this x transpose x and force them to be the identity. Similarly, forcing that the theta should be like theta squared should be equal to +1 just means that you have to pick these diagonal entries of x transpose x and force that to be the identity. And we can also force extra constraints, which are all function of this matrix, magic matrix x transpose x. So what I'm arguing is that this problem can be formulated exactly, except for the determinant constraint that I'm dropping, exactly as this problem, where the f is a convex quadratic function, and the other constraints are quadratic equality constraints. Now, this formulation, because of the quadratic equality constraints, is still non-convex. Quadratic equality constraints are non-convex. And the trick is pretty much always the same to get a convex relaxation. You take x transpose x, and you replace it with a full matrix Z. So rather than x transpose x, you use a single matrix Z, and you replace every x transpose x with a Z. Okay? For the matrix Z to be equal to x transpose x, Z should be positive semi-definite and should have rank D, which is the number of columns here in the number of rows here. Okay? So I'm rewriting instead of x transpose x the same problem as a function on Z, and now I'm realizing that this problem has a quadratic objective, linear constraints which are good, they're convex, semi-definite constraint which is convex as well, and the only non-convex is the fact that I want to enforce the rank of this matrix to be D. So in order to get a convex relaxation, I just drop the rank constraint, and I get a convex relaxation. So we started with a difficult problem to solve, combinatorial, non-convex, and so on. We ended up with a convex relaxation, which has the nice feature of being solvable in polynomial time and without need of any initial guess for the trajectory. Now the question is the solution of this convex relaxation going to be a reasonable solution for the original problem? We have a few results about that. I think there is more work to be done on this, but the basic result is that is about certification of robustness. So it's easy to get a result like if the solution Z star of the convex relaxation has rank D, where D, again, is the dimension of the problem, 2 or 3, then Z star can be factored into x transpose x, and x is the optimal solution of the original combinatorial, non-convex, truncated least square problem. In other words, you take Z transpose, Z star, you can just extract all the poses and all the decision about inlier and outlier. Put it in practice, this means that when the rank of Z is exactly D, all the outliers are rejected, and all the measurements selected as outliers will have small error. And also, we can guarantee that outliers are preserved, just because we said that the cost of having an outlier is smaller than the cost of having an outlier. So this is work done by C and Pierre-Yves in my group. And the nice thing is that in practice, we observe that in a domain, which is not huge this time, but in a domain in which the measurement noise and the number of outliers is not huge, Z star has more rank, as rank D. Okay? So that's similar to what the notion that I was telling you about certifiably robust algorithms. There is a setup, there is a common problem instances in which the percentage of outliers is not huge, in which you can solve the problem and you can certify that you got the best solution for that, in the sense that you didn't reject outliers, you rejected all the outliers. Yeah?
In those tests, were the outliers added as uniform noise on the truth, or did they include, now I don't want to confuse notation, but inliers and outliers of the objects, for instance? Like if I had pixels inside the object versus outside the object. Sorry.
So that's for this lamp. Yeah, so I think what we do is just pick random pair of poses, add a loop closure, fake loop closure between them, and set the fake loop closure to be some random measurement. So they are added at random. So set up here, you have like 2 examples for SLAM and structure from motion, and you get the pose graph, which is this stuff in green, and the outliers are all the lines added in red. Some rotation noise, which is comparable to real application. Translation noise, 0.1 meters, standard deviation. And here what I'm showing is that for increasing percentage of outliers, I'm showing how well we can reconstruct the trajectory of the robot. So this is an error, so lower is better. We're comparing our approach against a number of state-of-the-art techniques. Our approach is discrete continuous graphical model, which is the one in cyan at the bottom. And you can see it's pretty much flat, independent on the percentage of outlier, which is good. And we are comparing against a number of other techniques. RRR is a popular one, which pretty much for outliers larger than 10%. And if you're not careful about the way you do parameter tuning, we'll get like a quite large error. And DCS is interesting because depending on the parameter tuning, can get like a bad error or can get like good performance. So it's very sensitive to that. And by the way, like the default value for that parameter is, here are different values of the parameter, 1, 10, 100. The default that the paper suggests is 1, which is the one that doesn't work. Rotation estimation, that's like the same problem, but instead of estimating poses attached to the nodes of the graph, you just estimate rotation, is a popular problem which shows up in structure from motion. And here again, we're comparing DCGM, which is the approach which is down here in cyan, with a number of other techniques, and we can get like much better. The interesting thing here is that even when the rank is not D, even when the relaxation is not exact, the error is still better than the others, which is something that will need a little bit more investigation. We don't know why. Here, the only thing that is better than the proposed approach is the green one, which is the ground truth, like without outliers. Okay, so it's not another technique. Okay, more real results, like on the KITI dataset and standard SLAM benchmarking datasets. Here, the message is that this is our approach and the error for our approach, and this is RRR, another technique for different choices of the parameters. In general, we're doing better, although there are like setups in which there is no algorithm performing the best. And here I'm showing a video in which this is the ground truth trajectory of the robot, of the car. This is the least square estimate, and that's the robust estimate with our technique. And in red, again, you see like outliers, which are due to bad place recognition. So at the end, we have this DCGM idea, which is an algorithm which requires minimal to no parameter tuning. We just have to set DC bar. Does not require an initial guess because we end up having a convex relaxation of the problem. And it's the first example of certifiably-robust algorithm. So it's indeed feasible in certain regime to get this kind of certifiably-robust algorithms. I want to spend the next 10 minutes or so telling you results about certifiably-robust registration. The nice thing about this is that the results that we end up having, yeah.
So you're still assuming correspondences are given, right?
But can be wrong.
What's that?
But can be wrong.
So what extent does outlier rejection give you robustness to bad correspondences. And because they shouldn't come in just this Gaussian way, right? They come in some correlated way. So do you feel like you're also addressing the correspondence problem implicitly?
So the outlier and inlier decision will decide on the correspondences being good or bad. And if you're worried about if you can capture the correlation between inliers and outliers, I didn't tell that because I didn't have time, but you can explicitly model. If you know that there is some correlation there, you can also model that in the problem. So you can say that some correspondence is correlated to some other correspondence. That is about the SLAM problem. So, yeah.
Well, are you done answering the question?
I think so.
Sorry.
Yeah.
I was just wondering.
One more thing, like, the correspondences part will be clearer on the registration part. That's why I'm going fast.
I was wondering if you've tried augmenting the cost function to promote rank these solutions.
No, it's a good idea. I think it's a good idea. We tried, like, with some, you're thinking about nuclear norm and things like that, right?
What was the question?
If we tried augmenting the cost function with some cost encouraging low-rank solution, like the nuclear norm. I think there is a little bit of trade-off there because if you had, the problem is that if you get an optimal solution at that point, you cannot go back and guarantee that you're rejecting outlier or inlier because the cost function is something different at that point. So it's something to think about. So I want to wrap up and to do this quickly and talk about certifiably-robust registration. The registration problem is about finding the rigid transformation between 2-point clouds. And it's a common problem in object detect post estimation and scan matching. So the typical procedure to do registration, you have 2-point clouds that you want to match. The first step is that you extract features in these point clouds, which can be just point with high curvature. Okay, there will be some feature detector there that you can use. Second step is to match features that look similar. For example, you can attach some descriptor to each feature and then match features that have similar descriptors. And the last step is to compute the relative pose by aligning corresponding features. Okay. Really, what I want to look at is a certifiably-robust approach to compute the relative pose. So the state of the art here is that if the correspondences are perfect, so all the correspondences really match one point in the point cloud to the corresponding point in the other, then you can formulate again the outlier-free problem as a non-linearly squared problem. And good news there is that the problem is solved. There is a closed-form solution to solve the case without outliers. In the case with outliers, what happens is that some of the correspondences are wrong, this dashed line, in the sense that this point does not really correspond to that point in the other point cloud. And I believe there is a little bit of a dichotomy for the case with outliers, and the dichotomy is between fast heuristics, which are fast but do not provide performance guarantee and fail in the presence of large number of outliers, and global solvers like branch and bound or mixed integer programming, in which you do get guarantees, but in the worst case, they run in exponential time. So the question we ask is, can we develop a certifiably-robust algorithm that can tolerate extreme amounts of outliers and run in polynomial time? The formulation is the same as before. We have a truncated least square cost function in which the theta is deciding between inliers or rejecting the measurement as outlier. And again, it's the idea of the truncated quadratic cost. Go a little bit fast because I'm late, but what I want to show again is that the cost function essentially will try to maximize the number of inliers. For example, this solution for the problem will explain we'll have 3 measurements, 3 correspondences being inlier. Therefore, we'll have smaller cost than this solution, for example. Okay? So really, what the optimization problem is trying to do is to maximize the number of inliers. Does it answer or clarify the question that you had? Okay. So here, we have a similar convex relaxation. I will not show you like how to get the convex relaxation, but you have an idea which is pretty similar. It's like the version 2.0, what I was discussing earlier in the talk. So we propose this algorithm, which is called teaser, which is truncated least square estimation and semi-definite relaxation. And here I want to give you the teaser of teaser. So we start with this very difficult optimization problem. We are clever to reformulate it as a quadratically constrained quadratic program. There is a little bit of extra cleverness in the formulation with respect to the SLAM case. And we do a convex relaxation of it. I'm saying here the convex relaxation is non-trivial. Typically, there is a trivial way to get the relaxation of a QCQP. If you do the trivial relaxation, does not work well. Instead, I will show that the relaxation that we do has a pretty surprising performance, I believe. I spent 0 time on these. Guarantees are pretty similar to the SLAM case. If you solve the convex relaxation, you get a low-rank solution. You are solving exactly the original problem. And in particular, if you get a rank 1 solution when formulating the problem with a quaternion formulation, you are solving exactly the original combinatorial problem. And Hank, who is the mastermind of this paper, was also able to show that in some cases you can prove that you get a rank 1 solution. It's a very simple case, like no noise and outliers, unfortunately, but that's a good starting point. And this paper is accepted on RSS. There is probably 5 times more than what I'm saying. Check it out. It's pretty cool. In particular, here I'm talking about how to relax the rotation part, but the paper is talking about scale estimation and translation estimation as well. So I want to spend the last 30 seconds here with the results. So why I'm excited about this. So this is the results from teaser, and this is the level of outliers, outlier correspondences that we have in the problem, and the rank of the solution. The blue is the rank of the proposed solution, which is the proposed relaxation, and is always 1, meaning that the proposed relaxation is always tight. If you do the naive QCQP relaxation, it breaks pretty much right away after you have few outliers. And this, of course, translates in the fact that the rotation error for increasing outliers is quite flat for our approach, meaning that we are able just to reject all the outliers without problems. We did standard testing on the Stanford Bunny, which is a standard data set here. And these, I want to tell you a couple of things about these results. So first of all, these are results for outlier ratio up to 99%, which means you have 1% of good data, the other one is just clutter. Okay? And I'm showing the rotation error and the translation error for a number of approaches, including RANSAC, fast global registration, which is a state-of-the-art approach, and GOR, which is a branch and bound approach. And our approach is teaser, which is the blue one, so has the smallest error, both in terms of rotation and translation. And we are happy because it's at very low error, but we're also happy because this is a polynomial time algorithm. While the second best approach, which is the one in green, is GOR, which is branch and bound, is exponential time. So we're doing even better than an exponential time algorithm. So teaser, at the end of the day, is a first polynomial time algorithm that tolerates up to 99% outliers. I'm running late. This is to show that in practical, point cloud registration problem is not uncommon to have a really huge number of outliers. So it's really important to go to approaches which are resilient to huge number of outliers. So for example, in this problem, RGBD data set, you can get anything between 95% to 96% of outliers. And to tell you that these are indeed difficult problems to solve, I'm showing here an example in which we have the Stanford Bunny. We downsample it a little bit, and then we add 80% of outliers, 80% of random points. Do you guys see the bunny in the red? Kind of, yeah. So the algorithm is returning the optimal solution. It's certifying that these one in green are indeed inliers. And of course, this is a setup in which the algorithm, for the algorithm, is pretty easy. It's 80%. The algorithm is able to go up to 99%. Okay? And this is a very cool example, but we'll not go over it. If you have questions about multiple objects, just ask me. To conclude, I believe we need to go beyond perception algorithm that kind of work. We really need to do that to go beyond, to enable safety-critical application and to reduce the human supervision. And I will show you in this talk that outlier rejection is a key problem, and unfortunately it's inapproximable, but it's still possible to design certifiably-robust algorithms, and I show you 2 examples, one for SLAM and the other one for registration. What we want to do next is really to put out fast solvers to really enable large-scale solution of these problem instances. And since we believe that this truncated least square formulation is quite general, we would like to use it for other perception problems. We are still exploring that. Of course, look at some theoretical results to go beyond in approximability. So guys, I'm already late. I want to stop here, thank every student and postdoc in my group. They're really doing the hard work behind these slides. Thank the sponsor, and thank you guys for the attention. I'll be happy to take questions.
When you solve the STB relaxations of the correspondence problem, how often do you get a matrix that's actually rank D? And when it's not rank D, can you do some rounding to project it back to the feasible set?
Yeah, so first of all, that is problem dependent, right? In the sense that here what we can prove is that in some cases, when the noise is small or when the outlier is not, are not huge number, you do get rank D. So there are regimes in which you can prove it, but that's not true for generalized DP.
Can you elaborate a bit more on which are the specific conditions that usually led to like non-full rankness in your optimization problem? Like more like in a numerical sense, what does it mean to have more outliers in that sense?
The numerical addition, which?
What makes you kind of like break that rank condition? Like, what kind of like makes you have a higher rank? Can you like elaborate? Why does the solver find that to be the optimal solution sometimes?
Typically, the way you can prove this, I do not have like a huge intuition about that. Typically, the way you can prove this is that the rank constraint becomes redundant when you have no noise, in the sense that even if you try to solve it without that constraint, you still get like a rank D solution. And what you can prove typically is that if you start adding a little bit of noise, that remains true for a while. That's the only intuition that you have so far, that I have so far. Yeah.
So you dropped the determinant condition on the rotation matrices. Did that result in any problems?
For the SLAM problem, we did that like for many different types of relaxation. What turns out that in practice, you get a solution. So if you adopt the determinant constraint, you can get either rotation with determinant +1 or reflection with determinant -1. What ends up happening once you relax that is that either you are lucky, you get all rotations, or you get all reflections, for which you can change the sign and still get the right rotation. So it's not a big deal. And you can prove it that if you have moderate noise, will never happen that you have like a rotation and reflection as part of the solution. You can prove that formally. Yep.
So mine's kind of a general question back to like your 3 axes. And do you have a sense of whether humans can do SLAM well? So like if you put one of your grad students in the tunnels and told them to map it, could they do it? Or how bad are the computer results, like the other alternative algorithms to what a human could do? Or a sense.
I will definitely get lost in the tunnel, I can tell you that. Something that humans are much better doing is leveraging like multiple cues, like semantic cues, appearance, geometry, like combining all these. Definitely, like humans are much better. Probably on the SLAM side and on the just purely geometric side, what I was going to say is that I put humans there, but it's somehow like an unfair comparison in the sense that it depends a lot on this sensor that you put on board, right? Humans are constrained in the set of sensor. Contrary to what Elon Musk says, if I put a LiDAR, maybe like things might get better if you have like a mapping with LiDARs and so on. So it depends on the sets of sensor. Humans probably are not the best at doing SLAM, if that can answer.
I have a question.
Yep.
Maybe also a general question. So you've talked about perception because you work on perception, but I think I might not be the only one in the room wondering, what can we steal from you, right? So there are many other problems that many of us work that there's also hybridness associated with just, I don't know, planning, control problems, where that might not have to do with correspondence problems or outliers, but also other types of discrete changes in behavior. Why is this a perception talk and not just general optimization? Or
True. I think that if you have a problem, like even in planning, in which you're playing in particular with rotations and you're playing with binary variables, probably you can still apply this convex relaxation. Here there is something a little bit important about, again, both the binary variables and the rotation being something that you can express as quadratic constraints. And this typically results in good relaxations. If you see the same structure in a planning problem, probably you can do the same. Everything ends up being, you also need to be a little bit clever about the problem formulation in the sense that this truncated least square formulation that I have ends up producing, after you do a lot of manipulation, ends up producing quadratic cost function in the QC-QP case. So you need to find that kind of formulation for which the cost is ugly, but is not too ugly to reformulate it as something like a QC-QP, for example, which you guys do in planning as well.
So if I get it correctly, all of this is like an offline SLAM. How hard is it to extend these ideas? As in when I get a new sample, I decide maybe I can reject some of my past samples or maybe reject the current sample.
Yeah, the way I see this is it's true that right now is batch, right? You have all the measurements and you do it. The way I see it is that you can use it in a recovery stage. Like, if you detect some problem in your SLAM, you call these and you solve the problem that you have. Or it would be interesting just designing an incremental version of these. For example, you can do some gradient descent technique that as soon as you get more measurements, will try to improve the cost function and so on. It's definitely a good avenue for research. But right now, the way we are thinking about it is batch optimization is already difficult enough. So guys, before taking, if there is another question, I want to show you one thing about the multi-robot case. And it's a minor thing, but I believe if you guys are not convinced about this being something interesting or surprising, I'll show you what happens here in the case in which you have 2 point clouds, 1 point cloud A, which I'm showing here, and a point cloud B that in this case contains 2 copies of the object in A, but one of the 2 copies is a little bit noisier, okay? A little bit more noise. So in this case, the convex relaxation that we propose is still giving a rank 1 solution, so no problem. It's able to solve the problem and is returning the version with less noise because that's fits better the data, okay? The thing that is surprising is that something that we found out essentially a few days ago is that if instead you have the case in which the second point cloud contains 2 identical copies of the object A, what happens is that teaser, which is our algorithm, returns a rank 2 solution, and from the rank 2 solution, you can still reconstruct both poses, which is something that we found out is very cool. It's very early, but I think there is something there.
Yours is the inner step of an EM algorithm still, right? No?
This will optimize the theta's are the correspondences, and the rotation is the estimate of the thing. And the convex relaxation will solve that both theta and the R at the same time. There is no EM. So this is finding global solution for the correspondences as well. And
You're just deciding correspondences inlier or not. I mean, someone already gave you pairs, right? You're not generating correspondences between 2 arbitrary points.
if you have enough computation, I can consider all possible correspondences. I can still run this, right? Every point in point cloud 1.
Your inlier ratio going really, really quickly to 0, though.
99%. Yeah, I mean, it's a little bit aggressive as an approach, but yeah, typically you do have some feature matching approach that you use to get correspondences, right? But I do believe that probably also if you do brute force matching of every possible point in one to every possible point of the other, and you can solve the resulting problem, chances are this will work.
This is a fantastic discussion. So I suggest that we continue with it outside with food.
Thank
you very much,
Thank
Luca.
you. Yeah, thanks.